this morning we have Dr. Paul Roebber, who is here from the University of Wisconsin-Milwaukee, and he's going to give us a talk on his DTC visitor project that he's been working on, and it's titled Towards Improving Predictability of Cold Season Precipitation Type and Amount for the HRRR-TLE, which is the time lag, right?
TLE.
TLE.
Time lagged, yes.
Time lagged. Okay, see. I haven't had my coffee yet this morning. So anyway, so I will let Paul take it away. So
Thanks, and thanks for coming. I don't usually give seminars at 9. I'm sure you don't usually go to them at 9. So I hope the rest of you have had your coffee, unlike Louisa, and are awake. I promise you it'll be interesting. At least parts of it will be, because I don't think it's something that you've seen that often. Although the project is the HRRR-TLE, and with Isadora Yankoff and Trevor Alcott are the people I've been collaborating with, most of what I'm showing is sort of the nuts and bolts of what we are applying to the HRRR-TLE, which we're still in the process of working, which is why I have this picture, not quite the end of the road. We're very close to having results, but we don't actually have results for that part yet. But the methods that we're using, I think, will be of interest, and that's really what I'm going to be talking about. So the reason for focusing on precipitation type, obviously, precipitation type is difficult as a forecast, and it's also high impact in certain situations. I happened to visit Montreal just, I think, a few months after the big ice storm in the late 1990s, and it was really incredible to see the damage that was caused by that. And so I've published some papers on those kinds of icing events, and precipitation type has always been a problem of interest to me. So really the big question, that's why I put it big here, is how to extract maximum information from the HRRR. And so the TLE is one way to try to generate some ensembles. I know that that's sort of moving off to the side, and you're looking at more of a traditional ensemble for the HRRR now. But the methods that I'm talking about here actually apply to any sort of ensemble kind of forecast system. And so using the TLE is a good way to see what we can extract from it, and it might still provide some utility in any case. So the HRRR-TLE, if you're not familiar with it, it forms a kind of a poor man's ensemble with 3 members, time lagged. And I haven't looked at this in the HRRR-TLE specifically, but most, if not all, ensembles that I have looked at suffer from under-dispersion. And a lot of methods have been developed over the years to try to combat this problem. And under-dispersion obviously means that you're not really representing the full breadth of the probability distribution in the forecast that you're getting. And so there are various post-processing methods and various methods of directly in the NWP that are used to try to fix that problem. Post-processing can do a lot in a lot of different areas, and it turns out that's one thing that you can do also for under-dispersion. So really, I've been doing a lot of machine learning kinds of applications over the last several years, and in particular, the one that I focused on mostly is something called evolutionary programming. So I'll talk to you quite a bit about that and where I'm going with that, the latest stuff that I've been doing with it. And by latest, I literally mean some of what I'm showing today I've done in the past week. So it's really latest. Bias correction is a very standard bias correction, but it seems to be quite effective. It's the standard bias correction that I think is used at NCEP. Bayesian model combination, not Bayesian model averaging. That's a slightly different technique. It has some similarity to Bayesian model averaging, but I think is better in terms of at least how it poses the problem. And self-organizing maps, that's the one thing that although we were looking at it, we're thinking about using it for the HRRR-TLE, we're actually not, in the end, I don't think, going to be using that. But it's interesting, and I wanted to show a little bit about that and why we thought it might be useful. So let's talk about evolutionary programming. So the simplest way to think about it is it's using the principles of evolution to evolve forecast algorithms in the context that I'm using it. And so in this case, it's going to be NWP post-processors. It's actually an idea that's been around in computer science circles since about the 1960s, but it really didn't start to gain a whole lot of practical use until the 1990s when computer power was sufficient to really start exploring the ideas in more detail. And I actually came across this not in the meteorological literature, but in a sort of just a public interest book I was reading. And it was about complex dynamics, and it talked about this one experiment that a computer scientist named Danny Hillis did with evolutionary programming, where he wanted to sort a set of random numbers. And the metric of success for that is the fewest number of steps to sort the random numbers. Now, personally, I use something called bubble sort, which is what I used when I first learned Fortran programming, and it still works effectively enough for me, but computer programmers like to find more efficient algorithms. So what he did was he used this idea of evolutionary programming to evolve computer programs that sort this set of random numbers. And he found that his solutions were almost as effective as the expert programs that he was comparing them against. They were maybe 1 or 2 steps longer than the expert programmers were able to produce. The other thing he found out was that because he used a fully generalized structure for evolving these programs, he found that many times he couldn't understand the logic. He didn't know how they got the answers they got. So I really liked the first part of that, and I really hated the second part. And so I thought also that this is a method that could really have benefit for sort of the weather forecasting context. And so I began to think about it from my own experience as a weather forecaster and understanding how that works. And I devised what you're seeing here, blocks of if-then lines. And each line is executing that if-then statement. And so what happens, depending on the parameters, either the line can always be executed, the if-then is always satisfied, it's never executed, it's never satisfied, or it's executed only under certain conditional circumstances. So what you end up getting, instead of, in this case, 10 lines, you might end up with, say, 3 or 4 lines. The first line is a statement that will always be executed. So it's like a baseline of your forecast. And the second, third, and fourth might be conditionals. Under certain conditions, you're going to modify that baseline forecast based on whatever the information is. And so if you think about this from a weather forecast context, if you're thinking about minimum temperature forecasting, for example, usually you form some sort of baseline forecast based on air mass characteristics. So it's cold air moving in, it's warm air moving in. So that kind of gets you in the ballpark of where you should be for that forecast. But then you look at other details, like what are the radiative characteristics? Is it cloudy? Is it windy? How dry is that air mass? And that's going to adjust your temperatures either up or down based on what you find out from that. And that's the way these algorithms work. And I have applied them to a number of different contexts now. And I find out that, in fact, I can understand the logic because I can follow the if-then process like I would as a forecaster. So I think it mimics pretty well what forecasters actually do. But what I do to set this up is, based on that interpretable algorithm structure, I initialize it completely randomly. So what you're seeing there, all the yellow boxes and the blue boxes, those are all randomly constructed. So the variables come out from a master list of possible variables, things that from domain expertise you might identify as being relevant to the problem. But the algorithms may not use all those variables. It may select certain ones, certain combinations of them. And you'll let the process actually determine which ones will be used and what the combinations will be. I also have coefficients, which are modifiable. There are also operators, multiplication and addition. And because the coefficients can be positive or negative, you also get subtraction. I didn't do anything fancy like logarithms or division because, again, it becomes a lot harder to interpret the logic if you do that. So just keeping it as simple as possible. So they end up looking like sort of linear or multiple linear or multiple nonlinear regression equations with if-then conditionals attached to them. That's what the end result of this is. And so as it goes through, starts off with these random structures. So you can imagine that initially they're going to be pretty bad forecasters, and they are. But some of them are a little bit better than some of the others. And then by measuring that success or fitness, whatever your measurement is, in the case of temperature, it might be root mean square error. In case of a probabilistic forecast, whether it's temperature or precipitation or anything else, you might use a Breyer skill score or Breyer score or something like that to measure the fitness of those solutions. The most fit solutions are then allowed to produce the next generation of algorithms based on what the current generation is, using some sort of combination Mutations are also allowed because that's how you introduce innovations. Otherwise, you're just mixing stuff that you started with. So you need to have mutations to present new possible solutions. Now, what happens often with mutations is they're very destructive. And so a lot of the new solutions are even worse than the old solution. Those ones die out. But some of them occasionally will produce something that's actually interesting and good, and that will then persist to the following generation. So you get that new information passing through. And basically, you just repeat those steps until you satisfy some sort of convergence criterion, and then you have a set of solutions. This method, I usually start with about 10,000 random algorithms. I've done experiments with many more. I think I did one experiment where I had 500,000 or even more than that. I had to use the NCAR computing to do that. And I found out that having much larger populations actually did improve the forecasts, but not very much. And that was actually a DTC-sponsored study where I looked at that. And so it wasn't worth all the additional effort to actually produce those solutions, which were only marginally better than what you can get with 10,000. So out of those 10,000 possible algorithms, there's only a smaller subset that are most skillful and that are different from each other in some measurable way. And so those are the ones that I actually use then for any other sorts of post-processing like Bayesian model combination or generating ensemble distributions in any number of ways. I should point out that evolutionary programming is only one of many possible machine learning approaches that you can use. So that's why I say it's like searching some small subset of the library of all possible solutions. So this is getting us somewhere in that mix. And also, if you repeat this process, start from scratch over again on the same data, you'll get a different set of solutions. They won't necessarily be identical. And so one of the things I've introduced in some of the approaches I'm doing here is to do that, sort of retain the best forecast solutions in my initial run through, and then I start it over again, and then I update that list of the best ones based on the new run so that I can continually try to get something better. Obviously, there's a time when you have not much returning for that investment, and so you stop what you're doing at that. And so I'll talk about that approach also. So under dispersion, here's a classic example with a rank histogram. This is from the reforecast version 2 temperature. It's an 11-member temperature forecast. It's an 11-member ensemble. And so you have 12 ranks going from the lowest to the highest. And what you want, ideally, is that everything line up with this black line. Then it's a reliable ensemble. And what you see here are that the lowest and the highest ranks are much larger than any of the others. That classic yeast shape is a signature of underdispersive ensemble. And that means that in the lowest rank, the observations are frequently lower than what the lowest member of the ensemble is. And the highest rank, the observations are frequently higher than the highest member in the ensemble. And so you don't want to see that. You want to try to improve that because it means the PDF is very sharp, but it's not very good. It's overconfident, effectively. So using one particular approach of evolutionary programming, which I've been using on the bottom, compared to the same data, that's the rank histogram I get using that. So it's really reduced the underdispersion. It still is a little bit underdispersive. It's not zero. We can't expect magic, but it improves it quite a bit. And I'll show, using a slightly different approach than this evolutionary programming approach, I can actually improve that still further. So this is a paper that's in Press and Monthly Weather Review. I was looking at the reforecast data, and this graph here shows over the area that I was doing the ensemble evolutionary programming, shows the improvement in root mean square error relative to the reforecast version 2 forecast. I should point out that all of these are bias corrected, including the reforecast. So when I was showing this, that's actually bias corrected. That's after bias correction. And so the improvement here is relative to the reforecast version 2, which has been bias corrected. And you're seeing areas where you're getting upwards of a degree Fahrenheit improvement relative to the baseline. The baseline's not terrible. I think the error is around, if I remember, with bias corrections, around 3.5 degrees Fahrenheit. So you're talking about knocking off a full degree on that. So that's pretty significant. So what I've been thinking about now is something called coevolution, which is basically where you have multiple species in an ecosystem, and they're either in some sort of cooperative or competitive kind of relationship. And I've looked at both. So a cooperative relationship might be if you think about bees and flowers. So they're interacting with each other in ways that benefit each species. When it's competitive, it's usually a predator-prey kind of relationship. So here's an example of this where you've got crabs feeding on snails. Snails don't like that too much, and so they start growing harder shells and spinier shells. The crabs don't like that, so they grow more powerful claws. And so this arms race continues indefinitely, but they're each sort of improving their capabilities within the ecosystem. So I thought, well, that's a pretty interesting idea. And it could apply very nicely to an evolutionary programming context. And actually, I got this idea several years ago when I was thinking about coevolution, and I remembered a paper that was published in Scientific American way back in 1984. It was a very simple paper by Dudney in which he was looking, I think it was in the math recreations or computer recreations part of that journal. And he was talking about sort of sharks and fish. And so the sharks are the red and the fish are the green. And a very simple set of rules, he was able to evolve these populations on a domain like this. And what was interesting to me about that is the fact that you get this clustering in that domain. And the reason that's interesting to me is because if you think about having diverse ensemble members, you want them to be different from each other in some way, still good, but different. And if you think about Darwin's finches in the Galapagos Islands, you had a bunch of different birds that initially were the same kind of species, and they moved to different islands and they specialized their beaks according to the details of what they found on those islands. So they actually evolved in separate populations. And so having this sort of ability to push the algorithms around in this domain and have them evolve kind of separately might improve the diversity of the solutions you get. So that was the idea. Obviously, I had no idea if this would actually work, but I thought it was interesting to try. So I set up a whole ecosystem dynamics to do this. I'm not going to go through all the details here, but just a couple of salient points. First is the structure for the algorithms is the same for both predator and prey. It's the if-then structure I was just showing you before, except I'm only using 5 lines instead of 10, because I found in my other research that 10 is more than you actually need. Most often they're finding solutions with 5 or fewer lines. And so I thought I'll cut to the chase and do just 5 and improve the computational efficiency by doing that. What I'm doing here is I have the location of these algorithms on some hypothetical ecosystem grid, which is 100 by 100. Again, just an arbitrary choice, but it seems to give a lot of room for them to evolve in diverse populations. So if you imagine you're doing this on gridded meteorological data, you can still do this, but what I do is I apply a separate 100 by 100 grid for every single grid point. So each grid point in the domain you're solving would have this ecosystem separately from the others where it's evolving. And the reason I want to do it that way is because if you look across a geographic domain, there can be a lot of differences from one grid point to the next, and so I really don't want them to mix their evolving algorithms there. I mix them later when I'm doing Bayesian model combination. The food is interesting. I use the variables that the algorithms are producing as the food source for the prey. So they're hunting around for this food source, and all of the possible variables in the potential predictor list are available for them, but they consume them also, and they have to regrow back. So if you have a bunch of prey feeding in one area, it's going to eliminate a lot of the variable supply through overgrazing, and that will force them to move to other areas or to actually die out because they're just sitting in the same place. And so it keeps the ecosystem dynamics, keeps it evolving. And if they're not grazing in a particular area, those variable supply can build up while they're in an area. So if the sharks are chasing the fish into a particular area that hasn't been visited recently, then they'll have a lot of available food while they're moving through that area. The predators, on the other hand, accumulate their food reserves basically by consuming the prey. So they're consuming the algorithms. One set of algorithms is consuming the other set of algorithms. And they deplete that when they spawn. And the feeding strategy is pretty simple. The more successful, using your success metric, the algorithms are, whether they're predator or prey, the better they are able, in the case of prey, to find the food and to avoid the predators, and in the case of the predators, to find the prey. So there's that competitive predator-prey relationship that's being driven by the success of the forecast. So the more successful they are, the better they're going to be able to survive in this ecosystem. And for both predator and prey, that's the case. A couple other things. So this is what that curve looks like. This is how that success curve actually changes. Yeah, this screen is kind of low. Sorry about that. So basically on the bottom is the relative performance relative to some baseline. So that might be, say, the reforecast version 2. In the case of the convective occurrence studies that I've been doing, it's the auto nowcaster performance. And so relative to that determines how successful the predator or the prey will be in terms of those implementing those strategies. And so it either implements a strategy of avoidance of predators and finding food in the case of prey, or it follows a random strategy if it falls below this probability. And so there's a combination at any given time of prey that are doing both of those things, but the more successful the population is, the more they're able to be smart about what they're doing. Breeding occurs based on how successful they have been recently in obtaining food resources. And the clones, I'm not using sexual reproduction, which I have done in some of these studies. It does seem to add some value, but it's also more complicated, and so I haven't been doing that here. All I'm doing here is cloning. But the clones also produce mutations with some relative frequency, which is dependent on the success of those algorithms. So the more successful they are, the less probable they are of producing a mutation, because you've already reached some level that's pretty good. But I still want some mutations to occur, because you may still find something that's an innovation. And for the predators, it's the same thing. Also, I'm producing what I call atavisms, which are throwbacks. They're fully random algorithms, like when I first initialized the setup. So if you're, like, let's say 50 or 60 generations in, some fraction of these clones will actually not be clones. They will be some randomly generated algorithm. The reason I do that is because if you look at any population, maybe not in this room, but in some rooms, you will see that there are some people who are way over there. And so we want to have that sort of reflect what's going on here. And if nothing else, if they're prey, they can become a readily available food source for the smart predators. And if they're dumb predators, then that means those prey can escape more easily and survive a little bit longer. So it just gives you more of a diverse population again. And also, I've added this fairly recently, which is learning. So if you can't read it, you don't need to read the box anyway. It's learning. So basically what happens is, if either a predator or a prey is wandering in some neighborhood and they encounter an algorithm of either type, so a prey can find another prey or it can find another predator, if it finds one that's smarter than it is, basically it's performing better than it is, it copies one of the 5 lines in its algorithm and tries to adapt using that. Now, that's not always going to help it. Sometimes it won't even hurt it. It won't change anything at all if it's a line that's never executed. But quite often it does help, and you'll see the learning can produce smarter algorithms also. So it sort of helps keep the populations in sync to some extent, too, which prevents a die-out from occurring, which is another risk that can happen in these kinds of ecosystems. So this is what it actually looks like. If you train this, so the predators, the sharks are in red, the prey, the fish are in green. So this is the total count of algorithms at any given time through the generations. This is through 200 generations. And what you see are these wide swings in the population count. So the prey go up to this very large value, nearly 10,000 algorithms. And by the way, I'm not capping this. They can go up to whatever level they want. So it's really the ecosystem dynamics that's determining how many algorithms you can actually have at any given time. And so it goes up, and then it starts to fall rapidly, because you'll notice that there's a little phase lag there where the predator population naturally also starts to increase. Why? Because there's more food available for them. And so they start consuming them. And as that happens, as that population gets larger, all of a sudden there's a collapse in the prey population, and it swings down, and that, of course, leads to a phase lag collapse in the predator population. And then the cycle starts over again. But you can see it's not purely cyclical. There's differences from one cycle to the next. It's really got a sort of complex dynamic in it. And you'll also see the dotted line here represents the, in this case I was doing convective occurrence, so it's the CSI metric for that. And you can see over the first 50 generations or so, it really is improving rapidly. And after that, it stabilizes quite a bit, but still does improve a little bit later on. And that's typical of any of these evolutionary programs. Most of the really fast learning happens at the initial stages, because you're starting from a population that effectively is random and then starts to learn things from its environment and starts to produce better algorithms. And so really, it doesn't take a lot of training to produce pretty good algorithms. Really within the first 20 or 30 generations, you're already getting really good algorithms. And the rest is sort of just adding more detail to that, making it a little bit better. So it's kind of an interesting dynamic. And you can actually dig much deeper into that if you want to, and to see all the details about birth rates and death rates from different sources. The main thing to see from here is that this is the birth of prey algorithms. This is the number of prey that are being eaten at any given time. And so you can see there's this same structure that I was talking about before. As the population gets large, initially it grows very fast because there aren't very many predators around. They've collapsed already. But then as they reach this higher population and the predators start returning, you see more and more of the prey start to get eaten, and that leads to this collapse in the prey population. So it has a very nice dynamic. Also, there's some really interesting things if you sort of plot it in a kind of simplified phase space. This reminds me a lot of sort of chaotic time series that I've looked at over the years. I can't say necessarily that this is. It may be fully chaotic. It may be at the edge of chaos. You can do a calculation using a Lyapunov exponent, which I haven't done for this. I was just thinking about this the other day, but I thought it was pretty interesting. And I do know there have been some studies of simplified models. J.C. Sprott at University of Wisconsin-Madison has done a lot of that work. And he published a paper in 2004 with collaborators where he did show that you get chaotic dynamics out of these ecosystems. His model was different from this, but I'm seeing something similar here. So what does it look like? So here's the 100 by 100 ecosystem domain. And all the red triangles represent predators. All the blue triangles represent prey. And so initially they're randomly dispersed. This is at essentially time 0. That's what we start out with. So they're all random algorithms, randomly dispersed on this thing. So there's not any structure here. But very quickly, a structure emerges. Here's after 30 generations. So what's happening are the predators are chasing the prey, and the prey are getting away. And so they're sort of moving around. If you put this, I didn't do an animation. It's kind of fun to look at them, but I didn't do it because I never trust animations in a talk. But I'll show you a couple of sequences to show you that this does move around quite a bit. So it actually starts to set up that structure. This is after 100 generations. So they're pooling in these collections, just like I wanted, where you have these populations sort of setting up. And this is what the food distribution looks like at that same time. So notice, the yellows represent full food supply of every variable up to the max of 5. And the purples represent very little or no food. And of course, it follows exactly what you'd expect it to, which is where all the prey are, is where you don't have much food because they're eating it all. And where they haven't been recently, there's good supplies. So basically, when they get chased into those areas, or they're seeking it because they're not being chased, they will find a bountiful food supply to continue to produce the next generations. So it never dies out. It always has some access to something. And I've done this over 1,000 generations now, and I've seen that it still follows that same sort of structure in different forecast contexts. This is what the final stage on, or near final stage on one of these iterations was. So again, you see it's taken on a different kind of structure, but the same idea where you've got these spreading pools. It looks sort of like outflow boundaries, actually, spreading pools of predator and prey. And this is not that same ecosystem grid. This is actually the North American grid for the temperature data, and I just didn't put the geography underneath it, but longitude is on the bottom, latitude is on the top. And this is the performance improvement of the evolutionary programs relative to the reforecast after 10 iterations. And so already you're starting to see areas where it's improving quite a bit in just a few iterations. And so, like I said before, it really does improve quite quickly. It doesn't improve uniformly everywhere. In fact, where it seems to improve the most is where the forecast errors are the highest. So if it's already a good forecast, it's hard for it to improve it much. But if it's not a good forecast, it's an area that has climatologically high forecast errors, it improves it a lot more in those areas. So that's what we would hope to see. So the bias correction, I'm not going to go into a lot of detail here. It's basically the one that's used at NCEP. It's a weight decay bias correction. So just using the last few forecasts error, you can apply a correction to that in the last error. And over time, it basically adapts in some sense to what the most recent errors look like. And so I found this is actually pretty effective. It actually cuts a lot of the error out of both the NWP ensemble and the evolutionary programs. But the evolutionary programs add quite a bit more beyond that. And it's actually very simple bias correction too, which is a nice piece of it. So this is Bayesian model averaging. This is a figure from Raftery et al. In 2005. I know this is commonly used now in meteorology, I think primarily because of this paper. And it's a really interesting idea. And I was doing some research on it a few years ago, and I ran into something else called Bayesian model combination, which actually looks a lot like it in the sense that it combines a lot of these individual PDFs into an overall PDF. But Bayesian model averaging starts with the assumption that your individual ensemble members that you're planning to put together in some way, one of them is the data generating model, meaning it's the truth. And of course we know from hard experience that none of them are the truth. And Bayesian model combination says we don't know if any of these are the truth. In fact, none of them may be the truth, but what we're seeking is the best combination of those untruthful members to get the best possible forecast. So it starts from a different hypothesis, and then it produces it based on that. But it does do the same kind of thing. So that's what I've been using. And I found it's pretty effective. So just to summarize some of the experiments I've done so far, using coevolution, I found it improves the root mean square error averaged over the whole domain to about 2.95 degrees Fahrenheit. And as I said, the bias-corrected reforecast is about 3.55, I think, so it improves it quite a bit. That improvement is about 3% more than you get from the standard evolutionary programming approach. So coevolution has helped even more, and it improves 11.4% over the RF version 2. And probabilistic temperature forecast, because you can also do this probabilistically also, it's not just deterministic. And it improves the rank probability score by about 3.6% over the standard EP and over the reforecast by 6%. So it's doing what EP does, standard EP, but it does it better. So it's actually worth all this extra ecosystem dynamics effort. And if you look at the rank histograms, so on the left is the evolutionary program, the standard evolutionary program rank histogram. On the right is the reforecast version 2. Here's what happens when you do the coevolution. So it's actually cut by half again the number of excessive outliers from the standard EP. And there's 21% in the reforecast, a really large number of excessive outliers, down to 4.7% with standard EP and down to 2.2% with coevolution. So it really was very effective at doing what we wanted it to do. So I mentioned I'm looking at the auto nowcaster convective occurrence. I'm doing this in collaboration with folks at CIRA through NOAA MDL. And this is what one example forecast. These are issued every 5 or 6 minutes. And this is 1 hour ahead lead time. every 5 or 6 minutes is issuing a forecast of convective occurrence. And the black circles here, this again is a geographic domain. I just didn't put the geography underneath it. It's most of the United States from about, let's say, the Great Lakes east to the ocean, which is over here. So the black circles represent actual occurrence of convection in the observations, and the colored contours are the probability of convective occurrence issued by the evolutionary program. And so what you're seeing is it's lining up a lot where the areas are actually having convection. It's also producing some over-forecasting. So it does have an over-forecast bias. So we can look at that, how well it's doing. This is a diagram that I invented back in 2009, so if you're interested in it and you don't know about it already, I saw at the WAF conference. It's being used quite a bit now. It's published in Weather and Forecasting in 2009. And essentially what it does is it plots probability of detection on the y-axis against success ratio, which is 1 minus false alarm ratio on the x-axis. And from that, you can derive the CSI and the bias. So this is bias equals 1, which is an unbiased forecast. This is over forecast. This is under forecast. And these sloping curves here represent the CSI. So obviously where you want to be, and you never are, is right up there, perfect forecast. And what it really illustrates nicely is what Chuck Doswell and others have called the duality of forecast error, which is basically, if you think about operating at one particular level of skill, which is along this line, all you're really doing is trading off false alarms and probability detections. So either you want to hit more and get more false alarms, or you want to miss more and get fewer false alarms. And so when we're looking at this, the ANC for the test data that I had is down here. This is what the different forms of the evolutionary programming is producing. And so they're all up here. So what you do, if you look at this, what you're seeing is it has quite a bit more skill. And most of that skill is being derived from an increased probability of detection with still a fairly significant over-forecast bias. So a lot of false alarms, but not a lot more false alarms than the ANC already produces. So it's really amped up the probability of detection quite a bit. Oh, you could also look at Breyer's skill score relative to climatology. It's about 0.8, so that's pretty good. So one question you might have had is, can we make this adaptive? And if you didn't have it, I'm going to answer that question anyway. And the answer is yes. And it's probably not surprising, but because it's evolutionary, that you might be able to make it adaptive. And the way I do this is you train in this case it's a coevolution, but you train it standard way, and then you dump the whole state of the thing after you think it's fully trained. And then you just use a moving window, updated one forecast at a time, where you evolve the current population based on that moving window, and that becomes your forecast group. And so you just keep moving it over time. And so what I'm showing here, the red, green, and blue curves represent the maximum, mean, and minimum CSI from that population at any given time. And this vertical line represents the time when I improve one piece of the forecast information. So I sort of fictitiously improved the ANC, which is an input to the evolutionary program at this point, and I wanted to look at how long does it take for it to really start to feel the influence of that improved information. It takes about 200 cycles based on that experiment, which if it's going every 5 or 6 minutes every day, that's not very long. It's a day or so for you to really see the influence start to propagate into the evolutionary programs. It's also faster than that, really, because the CSI that I'm computing is based on the prior 100 forecast cycles. So that means at this time here, you've actually got a set of forecasts that are still before you had the improved information. So it's somewhat faster than 200 cycles. In any case, the end result is, yes, the information does get into the system, and it gets into it fairly quickly. So you could imagine setting it up in a way, in an operational sense, where you don't have to do the retraining that's often an obstacle for these post-processing techniques. You set it up, And once you've got it set up, you just keep running it through the cycling each time you're making a forecast, and you get something that will adapt to whatever information is that's coming in. So if you have a better model, if you have a new piece of information even, you can put that into the system, and it will start to allocate that as it sees fit to produce the best possible solutions. Self-organizing maps is something that I said we're not actually using for the HRRR-TLE, but I think is interesting. And so the idea is, okay, if you've got regime structures, here's a case of a dramatic evolution of the upper level flow that occurred in conjunction with ET transitioning NURI. And what we found out in that case was we had a really significant forecast bust because there were massive minimum temperature records broken because of this ridge structure that was set up compared to what the medium range forecast was suggesting. And so having some understanding of these regimes is important. So we've been looking at this. Andrea Honor is my student who's been looking at this with respect to standardized anomalies of PV on the dynamic tropopause as a way of characterizing sort of the flow structure and using that to classify hemispheric regimes. And what we've been particularly interested in is what are the transition matrices. So basically on the bottom, she identified 30 different clusters using that data. So on the bottom are the initial state of the flow in any one of those 30 bins for the cluster. And on the left is the final state after 30 days. So if you start over here at, let's say, 25 or 26, where do you end up with? These are the probabilities of where you end up with. A lot of low probabilities here and some higher ones here, which turns out, interestingly, it's a recurrence phenomenon for that particular cluster. It ends up coming back to where it started quite often. And these are, in fact, statistically significant. We did bootstrap testing relative to sort of the background probabilities, and we found that both these higher areas and a lot of the lower areas are statistically significant. So what does that mean? It means if you start down here, you have some sense both of where it's going to end up and also where it's not going to end up. So that's good information. It's better than sort of the background information that you might have otherwise. So it's a possible tool for extended range forecasting. We've also looked at this in context with teleconnections. And we found out that primarily they don't project onto any of the major indices exclusively. There are a few of them that seem to have elements of those teleconnection patterns in them, but are not exclusively those patterns. So they're more complicated than just those teleconnection patterns would suggest. Okay, so that was all that stuff. What about the HRRR-TLE? So, as you may or may not know, it's a time-lagged ensemble. So here's an example where you have the 8, 9, and 10Z forecasts, and you want to put them together to create an ensemble. Tim has actually been collecting the data, which he's finished collecting. And so these colored circles represent the different regions that we're going to do the evolutionary programming training in. So we identify those regions based on climate definitions. And the forecast variables that he's using for these precipitation phase and type are on the right. That's the master list of potential predictors. Again, not necessarily all of them will be used, and they'll be used in various combinations depending on what the algorithms think is the best way to use them. And we're looking at precipitation type, rain, snow, ice pellets, freezing rain. We're doing this in the evolutionary programming using a form of the Lodgett equation. So basically you can calculate all those probabilities. The evolutionary programming is calculating the x that's in the Lodgett equation. So basically you can, using that calculation, actually evaluate, using the Breyer score, the success of the forecasts for all of those categories at once. And so that'll be a nice, efficient way of training it to do these probabilities. We could then combine them using Bayesian model combination or something like that afterwards, and we haven't got to that point yet. So we'll see. For cases, we decided to look at cyclone cases. And so in particular, we're looking at storm systems that follow this sort of classic track. So areas to the north of the track may either be in frozen precipitation exclusively or there'll be some sort of transition zone through here, and then on the south side of the track, traditionally you would expect to see rain. So basically we're looking at areas through this kind of swath that will all be affected by these kinds of systems. And he's developed a master list of cyclone cases over the period of time that we have the HRRR-TLE data for to actually collect that. He's collected all the station data. So here's an example of one of those types of cyclones. This was January 10th, 2016. Lance Bozard isn't here. If he was, he'd probably tell us all about that case. But essentially, there was an area here. Here's the freezing line. There was an area here where there was mixed precipitation and freezing rain. Through here, it was snow back here, and it was rain over there. And that's what the next picture, I believe, shows. So basically, this is sort of like the target region for the really difficult stuff, but also you want to make sure that you're getting good forecast of snow where it's snowing and good forecast of rain where it's raining. So that's what we'll be looking at for all these sets of cases. So how are we going to do that? And I'm wrapping up now, don't worry. So the evolutionary program here is a little bit different. It's not coevolution, it's a simpler form. We're going to start with this because I always think you should start simpler first and see how well you do with that before getting to more complex things. And so what we start with is a random set of algorithms, the same algorithm structure of 10,000, population 10,000. They go through the training data, and then we chop off 20%, the worst performing 20%. I'm sorry, we take the top performing 20% and we allow those to clone and mutate, and those replace the worst performing 20%. Then we check a master list, which at the first step has nobody in it, but we look for the 100 best performing algorithms at that stage based on the cross-validation data set. And then we go back here and we do that again. And so then a new set is produced. And we clone and mutate and we check them against the master list, which now has a population in there. Some of them are going to be better than what's on that list. Some will not be. The ones that are better are sort of saved over there. But everybody goes back here. And you keep doing that. We do it for, I think in this case, we're doing it for 100 iterations, which seems to work pretty well. But then we're repeating it 5 times. So like I said before, what we do after we've done those 100 iterations and we've come up with our 100 best, we start over again. But we keep that 100 best list. So this whole process repeats for 100 new iterations. And if any of those new ones are better than the original 100 best list, they get replaced. And you keep going through it. We do that 5 times just to make sure, if you imagine sort of the topography of the solution space as being like the mountains over there, it's complex topography. You may be on some lower plateau in your original 100 best, and if you don't sort of reinitialize things and start again, maybe you'll get yourself into another area of the topography and actually get something that's a little bit better. And we do see that. I don't show it here, but we do see that happening. So what remains to do in this study? Tim has been working hard on interpolating the HRRR-TLE data to station locations. He's nearly complete. He keeps running into problems with Cheyenne, both caused by Cheyenne and himself. So he's not quite there yet, but he's working hard at it. He expects to have results, he tells me, within the next couple of weeks from that. And we've already set up the evolutionary programming. We've tested it, so we know it runs. So all we have to do is wait until this step is complete to actually run through the training. The training doesn't take very long either. We're using the simpler form, as I mentioned. We're going to apply bias correction. And then Bayesian model combination using the 3 trained sets from each member of the HRRR-TLE. So we only have the number of raw weights to the 3rd power to actually evaluate, which is very easy to do. When you start getting large, this number here represents the number of ensemble members. So if you imagine having 10 ensemble members, I've done it with 4 raw weights. You can do that pretty easily still. But if you get up to 20, it becomes computationally impossible. So it really grows very quickly. So you have to limit the numbers of members that you use. The way I've been doing this with evolutionary programs, which can produce, in my top 100 list, I have 100. I can't do W to 100 combinations, right? So it also turns out that a lot of the top 100 are not that different from each other. There's some that are quite different, but a lot of them are not. So you can actually filter those out and come up with, usually I use 5, so a set of 5 algorithms that are high performing but are distinct from each other in a measurable way. And I use that to combine them. I find that gives good results from the Bayesian model combination. So then we'll perform the verification and compare that directly against the HRRR-TLE to sort of form a baseline of how much we're adding by doing all of this. And that's all I have. So thank you. Lisa, yours, by the way, so Lisa's from Sweden, and she invited me when she was working at SMHI to come out there to talk about some of the stuff when I was very much at the early stages of it. And I gave a seminar there at 9 a.m., I think it was. It's the only other time I've done it.
Different time. My question is about your sort of predator-prey. You said one of the main motivations is that it causes structures.
Right.
Is there a physical motivation to have that particular structure, or could you use any structure and see similar result?
Yeah, I like doing it this way because it's sort of naturally producing it. Actually, in some of the other evolutionary programming I did, I set up what I called, what did I call them? I can't remember, but ecosystem domains, which were just arbitrarily defined based on variables.
So these transitions, they're Boolean statements with if-else
Right.
statements. But it seems like one interesting extension could be to use these transition probabilities that you created on the maps in the second part of the project, and use those transition probabilities to evolve your evolution forward. Then you would get some structure that's related to the uncertainty of the map.
Okay, I'm going to have to talk to you a bit about that more. It sounds interesting, but I don't fully understand how you would do that.
So rather than saying if else, you evolve your the evolution evolves due to transition probability rather than an if else statement. And the transition probability you have to construct first. But that I thought was an interesting approach.
Okay, I'm going to talk to you about that because I still don't understand you.
Any other questions for Paul?
Yes.
How long? You said it doesn't take too long to train, but how long is too long?
Well, so how long is too long? How patient are you? So this is what I'm training on. It's just just a laptop. It's not a very fast processor. To do for the convective occurrence data, which has 31,000 data points, of which I think 21,000 I was using for training and cross-validation. To do 200 generations during the training, I think takes like an hour or 2 hours on a laptop. Now, if you're thinking about this in an operational context, you're using a smaller window that you're moving. I've been doing this on the laptop with the adaptive form. It takes, I think, a few seconds, like 3, 4, 5 seconds to run the next forecast. That's the whole thing, both the training and the forecast. So it actually doesn't take long at all in an operational context where you'd use this. Yes?
Another question about predator-prey, which I think is amazing. You said that it never dies out. Do you have an explanation for that?
And you have to, yeah, let me elaborate on that. So when you go back to the Dudney paper, he found out that when he was doing it with his simple rules, they often did die out, one or the other. So you imagine, obviously, if the prey die out, the predators are going to follow pretty quickly. And in this case, if you have the predators dying out, then the prey are going to overgraze everything, and they will probably die out also. So there is a risk of that. So I can't say that there's a generalizable rule where it will never die out. So that's one of the interesting things that I'm going to be experimenting with the temperature data to see if that's true over all 60 by 30 points over the data I have. But when you set it up, you do have to be careful to set it up in a way that seems like it's going to be sustainable over some long period of time.
Because that's my next question.
Yeah.
Your set of rules is very specific. Did you optimize on that before?
A little bit of trial and error to make sure that when you're starting with roughly the right number of predator and prey, because you know it's going to go into that cycle and sort of adjust. I did find in some of the early experiments that you could get a situation where the predators would just kind of consume everything, and that would be the end of everything. And the most important thing is that you keep the predator and prey in balance in terms of their capabilities. And that's where I think the learning actually helps a lot. Because by learning from each other, they're actually sort of amping up their own abilities. And I think that's probably the key to it, although I haven't done any experiments to see if that's the reason why that's happening. Those are good questions, though, because it's something that we do run into.
You mentioned overgrazing, so does that mean that you do have the third component of like the food for the fish in your predator-prey model?
Yes. So the variables are the food for the fish.
Okay.
So you have a domain where initially on the domain there's a certain number, when you initialize it, there's a certain number of increments of all the variables at every single point. So any prey at any point can use whatever variable it wants at that iteration. But as it does that, it starts using up those variables. And if you have a bunch that are in the same place, because you can have more than one, by the way, I didn't mention this, you can have stacked prey and predators in the same grid location. So you could actually have a situation where you have a big collection all in one area and quickly overgraze that location. Well, they won't be able to find any food, so they're going to start seeking other locations where there is food. And while they're leaving those areas where the variables were available and no longer are, they grow back over time. So they can return to that place later on, but they can't just sit there. Now, does that help? I don't know. It seems like it does help improve the ecosystem dynamics. But I don't know if it actually improves metrics of forecast success. But since the overall framework is the ecosystem dynamics, you want to make sure that that works properly. So is it complicated? Yes. I think that's fair to say. Is it worth it? I think it is, based on the results I'm getting from it.
Any other questions?
Well, thank you. I appreciate you coming.